right, we are starting chapter 2, which is equations and inequalities. So today we are going to be covering one-step equations. So when you're solving an equation, there are specific steps that you need to remember while you're solving them. The first one is to find the value of a variable that makes the statement true. Okay. All right, to solve an equation, we need to isolate the variable. We need to get it alone. Okay. We need to isolate the variable. To isolate the variable means to have it by itself on one side of the equation, to have it alone. Okay. And then lastly, you're using inverse operations to isolate the variable. Now, what I mean by inverse operations is I'm talking about the opposites. The opposites. So when I'm referring to addition, the inverse operation would be subtraction. The inverse operation of subtraction is addition. Multiplication is division. And if you haven't already guessed, division is multiplication. All right? So when we're using the inverse operations, in order to get the variable by itself, we often need to do the opposite of what's being done. So for example, our first equation here, we have x minus 3 equals 5. So as I said before, we want to isolate the variable. So we want to isolate x. We want to get it by itself. So what's happening in this equation is we are subtracting 3. Now in order to get x by itself, we need to do the opposite or the inverse operation of the equation. So in this case, the inverse operation of subtraction is addition. So we would add. All right. So in this case, we have x minus 3 equals 5. The inverse operation, we would add 3. And since we added 3 to this side, we would add 3 to this side. All right. Negative 3 plus 3 is 0, so it would go away. So all we have left on this side is x. All right. And then 5 plus 3 is 8. So our answer would be 8. Okay, x equals 8. So in order to check our answer, we can take our answer and plug it back into the variable and see if the statement is still true. So if I were to plug 8 in for x, I would have 8 minus 3 equals 5. And we know 8 minus 3 does equal 5. So 5 equals 5. So we know that our answer is correct. Okay? All right, let's do another example. So we have x plus 4 equals 6. So the first step is we want to figure out our inverse operation, and our inverse operation of addition is to subtract. All right, so what I'm going to do is I'm going to have x plus 4 equals 6. And I'm going to subtract 4 because I want to isolate x or get it by itself. Okay, those go away. So x is going to equal 6 minus 4 is 2. All right, so that would be my answer. Now if I check that answer, plug 2 in for x, 2 plus 4 equals 6. And we know 2 plus 4 does in fact equal 6, so our answer is correct. All right, one more addition and subtraction. one-step equation before we move on to multiplication and division. So we have x minus 2 equals 7. So think about it, what my inverse operation would be, and then how I would solve it. So my inverse operation would in fact be addition. So I'm going to add 2 to both sides. And x is going to equal 9. Got my crazy x here. All right. And if you check the answer, we do know that 9 minus 2 does in fact equal 7. All right. So while we are talking about one-step equations or equations in any situation, there are a couple properties we need to know. The first one is the division property of equality. So the division property of equality states that if you divide each side of an equation by the same non-zero number, the two sides remain equal. So what that means is if I had, for example, let's say 2, or let's say 20 equals 40 over 2. Okay? If I multiplied this side by 2 and this side by 2, so go away, multiplied them by 2, so we knew that 20 equals 40 over 2 because 40 divided by 2 does equal 20. But if I multiply both sides or divide by both sides by the same number, I would get 40 equals 40. Okay? So that's true for both the multiplication and division property of equality. So the multiplication property of equality states that you can, if you multiply each side of an equation by the same number, the two sides remain the same. So if I were to do, 50 equals, um, I don't know, 100 divided by 2, okay, and I were to multiply again by 2, and multiply again by 2, both sides would equal 100. All right. So using that idea, we can actually solve problems that way. So if I have 5y equals 100, so going back to my inverse operations, now I can think about the relationship between 5 and y is that they're being multiplied, okay? So if my relationship between 5 and y is multiplication, my inverse operation is to divide, because that is the opposite of multiplying. All right, now my goal is to still get y by itself. So if I have 5y equals 100, I'm going to divide both sides by the same number, because my division property of equality says I can do that. So 5 divided by 5 cancel out, so all I have left is y equals 100 divided by 5, which is 20. All right. All right, we'll do another example. So we have 9x equals 36. My inverse operation of 9x would be to divide 9. Divide 9. So x would equal 36 divided by 9, which is 4. All right, now in this case, I have a division problem. Now I'm going to write the problem a little bit differently because this is how you're going to see it in your book a lot or in problems. So I'm going to write it like this. It means the same thing, okay? So I have 8 divided by 7 equals 63, which is exactly the same problem over here. I just wrote it differently. Now the relationship between A and 7 is division. So I'm going to do the inverse operation of that relationship, which is multiplication. So I'm going to multiply by 7 and multiply by 7. My 7's cancel out because 7 divided by 7 is 1. So A equals 63 times 7, which is 441. Okay? I'm going to do one last example before I let you go. So I have 12 equals R divided by 9. So I have 12 equals R divided by 9. All right? So my relationship between R and 9 is division, so I'm going to multiply. All right, so the 9's go away, and R is going to equal 9 times 12, which is 108. All right, so that concludes our introduction to Chapter 2 and the order of how you should solve one-step equations.